So welcome everybody to the virtual seminar in economic theory. This is our final seminar before the summer break. We plan to be back after the summer, so keep checking for updates. Today we are very happy to have Marina Halac from Yale, who's going to present her work, Rank Uncertainty in Organizations, which is joined with Elliot Lipnowski and Daniel Rappaport. And we're also very happy to have Elliot here, who's going to help with questions. And finally, welcome to Ilya Segal, who's our guest panelist today. So the format, again, of the seminar is we have a 1 hour presentation, and at the end, there is 15 minutes time for questions and answers, where you will be able to ask questions in person. So during the talk, you can post your questions in the Q&A function, the little bubble that you should be seeing at the bottom of your screen. And we will either read these questions to Marina during the talk, or Elliot might help and answer some of these. Or you can, if we don't get to the questions during the talk, you can answer them. You can ask them in person during the Q&A. Finally, the talk will be recorded. So in case you do not want to be recorded, don't ask live questions. Okay, I think that's everything. So then we can get straight to the talk. So Marina, yes, the screen is yours.
Thank you. Thanks very much. Thanks a lot for the invitation. Very happy to be, well, here at home, but speaking to you. And thanks a lot, Ilya, for joining, and Elliot as well. So as Julia said, this paper is titled Rank Uncertainty in Organizations, and it's joined with Elliot Lipnowski and Daniel Rappaport. And the paper is about moral hazard in teams. So it's about how to incentivize a team of workers to exert effort towards a common project. And the success of the firm's project depends on workers' efforts in a complementary way, so that a worker's effort is more productive when more other workers are also exerting effort. Now, commonly in firms and organizations, it's difficult to assess the individual performance of workers in a team. So workers are rewarded based on the overall project success. And this means that workers are going to face strategic risk, since the success of the project, as I said, depends not only on their own effort choices, but also those of others. And so a problem that is going to arise in particular is that workers may be reluctant to work unless they expect that others will also be working towards the common project, right? And so a natural question in this context is going to be, how can a firm ensure that workers will want to exert effort at the least possible cost? So what we are going to ask is, what is the firm's optimal incentive scheme that induces these agents to work as a unique equilibrium outcome? Okay, and so to ensure agents to work, to ensure that agents will work at the least possible cost, the firm will want to not only offer high rewards for project success to make effort worthwhile, but the firm will also want to adjust these rewards in a way that helps the firm to manage the workers' expectations about each other. So in particular, given the complementary efforts, the firm would like to make workers optimistic about the effort of other workers, right? And so questions that are going to arise are whether transparency about workers' rank and pay will be a good thing for the firm to achieve this, and whether pay inequality is going to be a feature of optimal incentives. Okay. So the firm, as I said, wants to ensure effort at the least possible cost. So what the firm would want to do is to provide assurance to a worker that his coworker will work. And so the question is, how can the firm do this? Well, what the firm can do is offer this coworker a very steep, a very high reward for project success that makes working a dominant choice, right? And so this logic is behind the seminal work of A.L. Winter. So in his 2004 paper, Winter is going to study the problem of how to uniquely implement effort at the least possible cost. And he's going to tell us that the firm should be specifying a ranking of workers. So basically, some workers are going to be, I'm going to call them high rank workers. They are going to be offered a high reward for project success so that they are willing to work no matter what others do. So they find it dominant to work. And then given that, now for the lower rank workers, it's sufficient to offer them a lower reward for project success, since I only need to ensure that they're willing to work, given that the higher rank workers are going to be exerting effort, right? And so what we see here is that the scheme is going to ensure effort, but it's going to be doing so by inducing discrimination. So in particular, even if I start with workers who are completely symmetric, I'm going to be favoring some of them with high rewards to provide assurance to the other workers that they're going to be working, and hence offering lower rewards to these other workers. And so even if I start with completely identical workers, I'm going to offer very differential, very discriminatory incentives. And this discrimination result is actually related to also seminal contributions by Ilya that I'll mention later. Now, for us, the relevant question is, to which extent do we think that this is going to reflect real-world firm compensation practices? And a key issue here is that this analysis in Winter's paper and this conclusion, as we are going to see, rely heavily on the assumption that the firm's contract offers are public, okay? So basically this assumes that the workers' pay and relative positions inside the firm are completely transparent. And this happens to be in stark contrast with the evidence and with the current debate about firm compensation practices. So there is substantial literature, so I skipped the references here, but we cite some academic and trade articles in the paper, showing that firms rarely internally disclose the contractual terms of their employees. And also they often discourage or even prohibit workers from discussing their contract terms with each other. This is typically illegal, but there are surveys where workers report that they face the threat of punishment if they share their contractual terms with coworkers. And there is also some recent work showing that this pay secrecy inside firms is further sustained by social norms. So this takes us directly to what is the contribution of our paper. What we are going to show is that this firm that wants to ensure effort at the least possible cost will indeed find it optimal to limit workers' information about each other's contract offers. So we are going to allow for private contract offers, and we are going to see that the firm's optimal incentive scheme is going to create what we call rank uncertainty, and we are going to define that more precisely. And the firm will leverage this rank uncertainty in order to better address the strategic uncertainty that agents face, and hence guarantee effort at a lower cost. We are going to show that the firm's optimal incentive scheme is unique, and it entails no discrimination. So in stark contrast with the case of public contracts, we are going to find that for any two symmetric agents, their bonus offers are going to be identical, For any two nearly symmetric agents, their bonus offers will be nearly identical. So what this is telling us is that once we allow for private contracting, discrimination is not only unnecessary, but it's strictly suboptimal for the firm. And we are also going to investigate how the degree of rank uncertainty and agents' ranks and compensation vary if we allow agents to be asymmetric in their cost of effort. And this analysis is going to give rise to this idea of an organizational hierarchy. So we are going to see that the firm's optimal incentive scheme will imply a hierarchy where workers of similar skill are going to be assigned to the same hierarchical level, and only those of sufficiently higher skill will be assigned to higher levels. And we are going to have predictions for how their pay and their rank uncertainty changes with their cost. Okay. So that gives you a brief summary of what we do in the paper. And so before I move on to the model and more details, let me say a few words about the literature. So the paper belongs to the literature on contracting with externalities, which was pioneered by Ilya, who's joining us here. And so the papers that I'm listing here in that literature, they share with us, most of them, this focus on unique implementation. So understanding what is the optimal unique implementation mechanism for a designer. Except for Winter, all of these papers assume that agents' actions are observable and bilaterally contractible, whereas we are going to be interested in a moral hazard setting where actions are not observable, and hence our benchmark is Winter's paper. All of these papers are going to assume public contracting in the case of commitment at least, and hence our main departure is going to be to allow for these private contract offers. And so, as I said, the main, the key departure here in terms of also of results is that Winter finds this important result of discrimination under public contracting. And I want to mention that this result is related to the optimality, more broadly, to the optimality of divide and conquer strategies that Ilya has shown in his work. And so a main lesson from our paper will be that this result is overturned once we allow for private offers. This idea that introducing uncertainty can help the firm appears in previous work. So in particular, Elias and Spiegler and Morilla and Yamashita, they consider variants of Winter's team problem, and they allow for some randomization in the contracts, as we are going to do. But they are going to impose certain restrictions on the space of contracts that essentially rule out the main questions that we ask. Our paper also relates to a literature on information design, because we are going to be allowing the firm to design what information workers have about other workers' contract terms. And so in particular, there is, as you can see, a very recent, all these papers are 2020, a very recent set of recent and growing literature that studies persuasion in multi-agent settings under adversarial equilibrium selection. So namely under the idea that the equilibrium that agents are going to play will be the worst possible equilibrium from the viewpoint of the designer. And we can show that that corresponds to our solution concept of unique implementation. The main departure from this literature, of course, is that we are going to be designing not just information, but transfers and the information that agents have about those transfers. And then, of course, there are broader literatures to which we relate, studying from different angles the issue of incentives and discrimination, as well as the role of hierarchies in organizations. Okay. So I think I can now move on to the model. So the model setup is going to be a very simple setup. We are going to have a principal who offers contracts to a set of agents. I'm going to describe the contracts in the next slide. With some abuse of notation, we'll denote by capital N both the set and the number of agents. And each agent is going to then see his contract offer and is going to choose whether to work or shirk. And this is a private choice, it's hidden action. Shirking is costless and working is costly. So for agent I, the cost of effort is denoted by CI, which is strictly positive, but can be different across the agents. And so each agent chooses privately where to work or shirk, and depending on these choices, the principal's project can either succeed or fail. And this is going to be the only outcome that is both observable, and it's also verifiable. And so this project outcome is going to be determined by this production function P. I guess if I do this, you see this, right? When I move my, yeah. So this production function P, which is going to map from the set of agents who choose to work to a probability between 0 and 1, which is the probability of project success. So P of J would be the probability of project success when agents in set J choose to work and the rest choose to shirk. Okay. We are going to take this production function P to be strictly increasing. That means that effort is productive. So the more workers choose to work, the higher the probability of project success. And we are going to take the function P to be strictly supermodular. And that's going to reflect the idea that these agents' efforts are going to be complementary. So an agent's marginal product of effort, his contribution to project success from working, is going to be larger when more other agents are working. Okay. All right, and so then based on the project outcome, either success or failure, the agents are going to be paid according to their contracts. Now, we are going to assume that agents are protected by limited liability. And so given that, and given that the only contractable thing is whether the project succeeds or fails, without loss, the principal will be simply specifying bonuses for the agents contingent on project success. And in the case of failure, the agents are going to get 0 payments. Okay. Now, as I anticipated, we want to allow the principal's bonus offers to be private. And so this is a way in which we can formalize this idea. So the principal is going to commit to an incentive scheme, sigma, that we are going to describe with 3 elements. Capital T is going to be a product set of types for the agents. So capital Ti is a set of types for agent I, which we are going to take to be finite. We are going to have a distribution over type profiles. That's going to be Q. And then we're going to have a bonus rule. So we have here a vector of BI. BI is a function that maps from the set of types of agent I to R plus. And so basically, it's going to tell us for any realized type of agent I, let's call that little ti, BI of little ti is the bonus that this type ti is going to receive if the project succeeds. Okay, so basically the principal draws a profile of types and each agent learns his own type, and through that type that he learns, he has realized, he learns what is his success contingent bonus. Now the agents may face, they know their own bonus offer, but they may face uncertainty about what are the bonus offers of other agents. And that uncertainty is going to depend on the principal's choice of Q, namely the correlation between the agent's types, right? And so this can embed the case of public contracts. That would be a case where for each agent and each possible type realization of the agent, once the agent observes his type, there is a unique profile of other agents' types that the agent knows can realize with positive probability. So I can tell what the types of the other agents are. Okay.
Sorry, Marina, I think
yeah,
it's a good time to ask because I am a bit confused by the terminology you're using.
Okay.
I think I understand the model, but when you say public versus private, I mean, my understanding is for this model, it's important that Q itself is public, right? So there's a commitment to Q. To the
absolutely, yes,
distribution.
Absolutely.
As opposed to, so I mean, there's private, there's a commitment to private randomization, but the
yes.
contract is Q. In some sense, Q is the contract, and it's a public commitment. Because otherwise, if there's no public commitment, wouldn't the principal be tempted to then kind of renegotiate? You know, like suppose that you can announce Q and then you can, like to a given agent, you can change it. You would probably want to do that, right? So that's what I would call that situation in the case of private contracts. Is it correct?
Okay, so let me, right. So the way we think of this is, you are completely right that I'm committing to this incentive scheme. So I'm committing to a queue. And so in that sense, Q is public, as everyone knows Q, right?
Right.
So Q is the distribution. What agents don't observe, and that's what we call private here, is the realization of the type profile. So in some sense, suppose, these types are just a convenient tool here for describing the scheme, but of course we could encode the types in the bonuses, right? And so what's key here is that I don't know what bonus you were offered, right? So we are both in this team. I see the bonus that I was offered, and I don't see the bonus that you were offered. I do know the distribution, right? I know what bonuses you may be offered with what probabilities, and the principal is committing to that, and that's very important. So so maybe for those who are listening, so Ilya considers the case of private contracting without commitment, and it's a very different problem, right? It's a problem where you have this renegotiation that you are describing, and where you would not be able to commit to a randomization, in the sense that, in particular, on path, agents would face no uncertainty on the bonuses of other agents. But here, precisely because of what you're saying, agents on path face this uncertainty about what was the bonus, or in our language, the type, right, that was realized for the other agents. And I guess the natural follow-up question that you might have is, like, to which extent the principal can commit to this randomization, and that's always a fun question to discuss when we have commitment to randomizations. I'll try to convince you that in our setting, actually, it's not a very problematic issue. We'll see how much I can convince you of that, but for that, I want to get to some results before, but we'll get there, hopefully.
All right, thanks.
Good, sure. All right, so because I have assumed the types to be, oh, I see something in the Q&A. I should ignore that, right? Or should I? I'll just ignore it. I'll let Elliot.
I mean, I guess it's sorry. I guess it's a quick question. No, it's answered.
That's fine.
Okay.
I'll just let you tell me when I have to pay attention to those things.
You just ignore all of this.
I'll just focus on one. It's enough for me. Okay, so capital TI is a set of types for H and I. We took this to be finite. These are just labels, as I said. And so without loss, we take that to be a subset of the natural numbers. And then we can throw away any types that have 0 probability. So I'll also, without loss, take QI, the marginal of Q along dimension I, to have full support on capital TI. Okay, so these are just normalizations. All right, so the principal commits, as we were saying, to this incentive scheme. And this incentive scheme is going to induce a Bayesian game among the agents, right? So think of this game as it's a game where Q is the common prior on the space of types, and where each agent is going to be simultaneously choosing where to work or share, with a payoff which is equal to the expected payment minus the cost of effort if he chooses to work. And so agents are risk neutral in our setting. And so we are inducing this Bayesian game. And so we are going to say that an incentive scheme induces an equilibrium when this is a Bayesian Nash equilibrium of the induced Bayesian game. Now, what is the principal's goal here? Well, as I said, the principal wants to ensure that these workers are going to be exerting effort. And he would want to do that at the least possible cost, okay? So the principal would want to ensure that there is a unique Bayesian Nash equilibrium in the induced Bayesian game where all the agents choose to work. We run into the problem of the open set because these bonuses are continuous variables. I can keep lowering them until I hit indifference. And so we are going to resolve this by brute force, as it's done in the literature. And we are going to have this definition. We are going to say that an incentive scheme sigma uniquely implements work, which I'll abbreviate as UIW, if for all epsilon strictly positive, all types of every agent working is going to be the unique Bayesian Nash equilibrium of the Bayesian game induced by this scheme sigma when I increase the bonus for each agent type by epsilon. Okay, so this epsilon won't really change any of our results, but one way to think of this is as a refinement of Bayesian Nash equilibrium, where basically what we are saying is that if agents are indifferent between working and shirking, they're going to be working. Okay, so that's all. So now that we have this definition, we can write the principal's problem as we have in this program here. So what the principal wants to do is choose an incentive scheme sigma that uniquely implements work and that minimizes the expected cost, the expected incentive cost for the principal. So we have an if, in general, we want to achieve the minimum. And what I have here is that is the principal's expected cost from this incentive scheme, given that also that all the agents are working since this scheme is uniquely implementing work, okay? And so this is very simple. We have, what is the principal's expected cost? Well, the principal will have to pay these agents the bonuses in the case of success. So P of n here is the probability that the project succeeds, given again that all the agents are working. And then I'm going to add over the agents I in the set n, and these are the expected bonus that I have to pay to the agents, taking the expectation over the types. Okay. So that's the principal's problem. That's the problem we are going to be dealing with. But before we solve this problem, it's going to be instructive to illustrate the intuition for our basic insights with a simplified example. So that's what I'm going to do next, okay? Oh, before I do that, let me just make two quick remarks here that might help to understand how we solve the problem. So the first quick remark is that I just want to say this is the same solution concept that Winter uses to solve his problem, the difference being that we have a Bayesian game because we have private contracting compared to him. And the second quick remark is that we have chosen to the solution concept, which is a unique equilibrium implementation. But we can show actually that in our setting, this is equivalent to requiring that all agents working be the unique rationalizable outcome. And this follows from the fact that I have a supermodular production function and the limited liability that implies that for any incentive scheme, the game induced by the incentive scheme is going to be a supermodular game. And so we can just apply Milgram-Roberts to show the equivalence. Okay, and so it might be helpful when we go over the results to remember that this is the same as solving for the unique rationalizable outcome to be everyone to be working. Okay, so now let's go to this very simplified example that will show the basic insights of our model. So for the simplified example, I'm going to just take two workers and I'll assume that they are completely symmetric. So they will have the same cost of effort and the same contribution to project success. And we'll also take a particular production function, which is the same that Winter takes in also his leading setting. And so to think about this production function, let's think about the following. Let's imagine that each of these two workers has a task to complete. And the project of the firm is going to succeed if and only if both tasks are completed, okay? Now, if a worker works, he completes his task with probability 1. If the worker shirks, he completes his task with probability P. And so this being independent across the workers. So that means that if both workers work, then the project is going to succeed with probability 1. If both workers shirk, the project is going to succeed with probability P squared. And if only one worker works and the other shirks, the project succeeds with probability P. Okay, so very simple for this example. So let's take this setting and let's start by considering public contracts. So let's forget about these types and this randomization. And let's suppose that all the firm has to do here is specify a bonus contingent on success for each of these two agents. And also let's take another step back and imagine to start with that all I want to do is induce work as one equilibrium of the induced game. So not necessarily the unique equilibrium, okay? So what do I do in that case? Well, in that case, all I need to do is make sure that the bonus that I offer makes each worker willing to work when he conditions on the fact that the other worker is also working, okay? And so the bonus, the lowest bonus that ensures that is going to be given by BL here. So BL is equal to the cost of effort divided by the marginal product of effort when I condition on the other worker also working. right? So if the other worker is working, I increase the probability of success from working from P to 1. So if we offer this bonus BL to both workers, then there is going to be an equilibrium in which both workers work. However, the problem is that there is also going to be an equilibrium in which both workers shirk. And this is going to be true even if I increase the bonus BL by some epsilon, okay? And so we take the view that the firm is not okay, which is letting this to be randomly selected which equilibrium will be played. And so let's take the view of I want to ensure that the good equilibrium, the work equilibrium, is the one that is going to be implemented. So how do I do that here? Well, to make sure that that's the unique equilibrium, what I have to do is make it dominant for one of these workers to work. So make sure that, let's say for worker 1, we offer a bonus that is high enough that he would be willing to work even if he thinks that worker 2 is going to be shirking, okay? And so that bonus is equal to BH. BH is equal to the cost of effort divided by the marginal product of effort when I'm conditioning on the other worker shirking, which by the complementary efforts is going to be lower than the marginal product of effort when I condition on the other worker working. And so BH is going to make work dominant for worker 1, but now that this worker 1 finds it dominant to work, I can now offer the low bonus to the other worker, to worker 2, and make sure that he will also want to work because he's going to be conditioning on worker 1 exerting effort. And so in a setting where the firm can only offer public contracts, the least cost incentive scheme that ensures work in this example is going to be one that pays BH plus BL in the case of success, which has probability 1 in this very simple example, right? And what's important and illustrates this result by Winter is the fact that this scheme is going to be discriminatory. So even though I said that my workers are completely identical, you can see that one of them is going to get a high bonus and the other a low bonus. I could potentially randomize ex ante over which one is going to get the high bonus, but at least ex post, there is going to be discrimination. The main intuition here is that I'm going to be favoring one worker with a high bonus in order to provide assurance to the other worker that this worker will be exerting effort. And once I provide that assurance, that allows me now to incentivize the second worker to exert effort with a lower bonus pay. Now it turns out that the firm can do better here by introducing uncertainty. And so let me try to show you that in the simplest possible way, okay? And so the simplest possible way for us is to think about the following. Let's suppose that for one of these workers, the firm is going to offer a private contract with a random bonus. So specifically, let's say that worker 1 is going to be offered either the high bonus or the low bonus, each with equal probability. Now, worker 1 knows which bonus he's offered before he chooses where to exert effort or not, but worker 2 only knows the distribution, as we were saying before with Ilya, the distribution of worker 1's bonus offer, right? And so what happens now? Well, if worker 1 is offered the high bonus, then he finds it dominant to work. Worker 2 knows that that happens with probability 1/2. So now what the firm can do is offer worker 2 a bonus equal to BM, as we see on the slide, which makes him willing to work when he conditions on worker 1 working with probability 1/2 and shirking with probability 1/2, right? So that's the worst case belief that he can have is that worker 1 is going to be shirking with probability 1/2. So this will ensure that worker 2 is also willing to work. But moreover, now that worker 2 is going to be working, now that provides assurance to the low bonus type of worker 1. And I know that even when worker 1 receives the low bonus offer, he will also want to work. And so this is a scheme now that is also going to ensure that both workers are going to exert effort as the unique Bayesian-Nash equilibrium of the induced game. But we are doing things differently compared to the previous case in that now instead of favoring one worker to provide assurance to the other worker, we are going to build this assurance in a mutual way, right? So we are going to have the high bonus type of worker 1 provide assurance to worker 2, and then worker 2 is going to provide assurance to the low bonus type of worker 1. And what we are going to see, one of the main insights of our paper, is that providing this assurance in a mutual way can be a good thing, because it turns out that this assurance is most valuable for a worker, is most valuable in the sense of increasing his incentive to work, exactly when this worker is very pessimistic about the other worker's effort, okay? And so we can verify that quite easily here. So in this example, we can verify that the medium bonus, BM, is strictly less than the average of the high and low bonuses. And so what that tells us is that when I move from the public contract case to this very simple private contracting scheme, I find that the total average payments that the firm has to make decrease. And so immediately this is telling us that public contracts are with loss of generality, meaning that the firm can do better with private contracting. We can also verify that the medium bonus is strictly between the low and high bonus, and I guess that's why we call it the medium bonus. And what this says is that in this example, as I move to private contracting, namely as I lower transparency in this firm, I also lower the degree of discrimination between the workers, right? So this scheme that we have proposed is less discriminatory than the public incentive scheme. Now, this doesn't tell us yet that the optimal incentive scheme under private contracting will be less discriminatory, because it turns out that this scheme that I just showed you, this very simple scheme, is not the optimal scheme in this setting. It's just a scheme that we chose to illustrate things in a simple way. But what we are going to show you, we are going to solve for the optimal incentive scheme, and we are going to show you that it not only reduces discrimination relative to public contracts, it indeed eliminates discrimination. Okay. All right. So that was the simple example, and now with this insights, these basic intuitions in mind, we're going to move to the general model. So in the general model, what is different? Remember, we have any number n of agents. They are not necessarily symmetric, so they may have different costs of efforts or contributions to project success. And we have a general production function that which is required to be increasing and supermodular. Okay. So the way we proceed is as follows. So we want to solve the principal's problem. So we are going to proceed in the following way. First, we're going to define a simple class of incentive schemes that will simplify the principal's search for the optimal scheme. Then we are going to derive an auxiliary program that fully characterizes the principal's optimal value in a convenient way. And then we are going to show that that program also characterizes optimal incentive schemes by pinning down the unique optimal bonus offers. Okay, so let's get started. So what is this simple class of incentive schemes? This is what we call ranking schemes. So as you're going to see, this idea in Winter's paper that the firm should specify a ranking is also going to appear in our work. But the key difference is that the ranking can be uncertain in our setting. And so we are going to say that an incentive scheme sigma is a ranking scheme if the following two conditions hold. So first of all, no two agents can ever realize the same type. So that's what the first condition says. It's inconsequential without the second condition, but the second condition will say that for every agent I and every type Ti of agent I, the bonus is going to define to satisfy this equation. And this equation says that the bonus will make this type Ti of agent I indifferent between working and shirking, under the hypothesis that agents of lower type work and those of higher type shirk. Okay, so you can see this here. I have the cost of effort on the right-hand side. I have this bonus, and the marginal product of effort is taken to be such that I'm conditioning on lower types working and higher types shirking. And so I compare the probability of success when I join the types who are working versus when I shirk.
Maria, I think I understand what you said in words. I just don't quite understand the notation here, but maybe it's okay as long as I understand the word, because for the notation, don't you want to add over like all the other agents or something? I mean, is it like a shorthand notation or it's actually formal?
Oh, this is
Like
just for
P,
every
the probability.
agent I. For every agent I.
No, but J, like the probability of J. So the probability is taken. Maybe I'm overthinking it, but
oh yeah. So I think it's just notation. So this is the probability of project success when all agents J with a lower type work. That's what it means.
Right? Okay. All right. I just
So it's a set of it. This is a set defined. It's a set of all agents J whose type Tj is less than Ti.
Okay.
I is in the first set, not in the second set. That's why the difference is non-zero.
Oh, this is what. Oh, I'm sorry. Is this what you? So notice that this is strict and this is less or equal.
No, I understand that part. I just anyway. I mean, I understand that at the level that is sufficient. Move on. All right.
Okay. Yeah. So P is a function of a set, and so this defines that set. I don't know if that helps, but
no, I understand. Okay. Yeah, I understand. All right.
Okay. Yeah, sorry, maybe I went too fast at the beginning, but I'm sure conceptually you understand what I'm saying. Okay, so this is how we define a ranking scheme, and ranking schemes take this very simple form, which is going to be useful. Well, first of all, we can very quickly verify that every ranking scheme will uniquely implement work. So what is the idea? So for every type, I'm specifying the bonus so that he's indifferent between working and shirking when lower types work and higher types shirk. And so that means that if I add epsilon, he will strictly prefer to work. And moreover, because of complementarities, this tells me that he will strictly prefer to work when at least the lower types choose to work. And so then we can prove that this uniquely implements work by just iterating on the type. The lowest type finds it dominant to work. The second lowest type finds it dominant to work, even that the lowest type works, and so on and so on. Okay, so that part is quite simple, but the main reason why ranking schemes are useful is the second part of this lemma, which shows that if I have any incentive scheme that uniquely implements work, then I can find a ranking scheme that weakly improves the principal's objective. So namely that weakly reduces the principal's expected incentive cost. Okay, and so this is useful because it's telling us that we can simply search over ranking schemes when solving the principal's problem. And so very briefly, I'm going to give you some intuition for the second part because I have this beautiful graph that I cannot take credit for because it's, I owe it to my co-author Elliot, that is going to describe the main idea. So what is the main idea? Give me any incentive scheme that uniquely implements work. It has to be that for every type of every agent, there is a stage at which shirk becomes dominated, right? Because otherwise I could find an epsilon such that I have an equilibrium that is not everyone working, right? And so what I'm doing here is, let's imagine that I have 3 agents, blue, red, and green. And for each agent, I have 3 types, circle, square, and triangle. And so what I'm depicting here is the stage at which shirk becomes dominated for each of these types. So now I want to index the types according to this stage, so 1, 2, 3. But I also want to break ties in an arbitrary way. Okay, so let's just break ties like this. I'm sorry. And so after doing that, I'm going to relabel types to reflect this new order. And now I'm going to assign bonuses to each type exactly as in the definition of a ranking scheme. And so it's quite simple to verify that by doing this, we are systematically lowering the bonus that we offer to each agent type. There are 2 possible reasons for this. One, of course, is that there could have been slack in the original scheme in the bonus offers. But more importantly, the main reason is that we're also changing the incentive constraints by weakly increasing the number of other agents that a given type is going to be conditioning on to be working when he chooses where to work or shirk, right? So if I take the triangle type for the red agent here, in the ranking scheme that I constructed, he's going to be conditioning on all types of the blue agent and the square type of the red agents to be working, whereas in the original scheme, he was only conditioning on 2 types of the blue agent to be working. And so given the complementarities, I can now offer him a lower bonus payment. Okay.
Marina, another way of thinking about this, I think, is that can you think of this as a supermodular game, including agents type cross agent? So each agent of each type is a separate, and then you can just apply existing thing about like what I did, like top thesis, like rationalizability in supermodular games, where kind of the same thing. Like you need at each stage one type of each agent to move forward, and that's how. Okay.
Absolutely. I guess this is our colorful way of saying that, but but you're absolutely right. Yes, that's exactly correct. Yes. Yes, very good. Thank you. Thanks. Good. So now, clearly, once we are looking at ranking schemes, we know that, sorry, there you go. So we know that an agent's incentive to work under a ranking scheme will depend on his belief about, which agents have realized a lower type than his own, right? And so to make that explicit, let me introduce a little bit of notation. So I'm going, let's call capital pi the set of permutations on the set of agents n. Then each profile of types t without ties is going to induce an agent ranking pi of t. So basically we want to get rid of the type labels and we just care about the order, right? So if you're the second lowest type, now you have rank 2. So that's what the agent ranking is going to tell us. Now there is going to be a distribution over the agent rankings that is going to be induced by a ranking scheme sigma. Let's call that distribution mu sigma. And then each agent, when he's learning his own type, he may be learning something. He's getting a signal about the realized ranking. And so he's going to have a conditional belief, which we call ranking belief, and which is here, mu I sigma conditional on ti, okay? So now, given all this notation, what I want to do is I want to define the following. Let's fix a ranking belief mu I for agent I. Then now this fraction should look familiar by now. I'm going to write here what is the minimum payment that I need for this agent to be willing to work given his ranking belief mu I. And so what this is equal to? This is equal to the cost of effort divided by his expected marginal product of effort, given that he's conditioning on all agents who are placed ahead of him in the ranking working and all other agents shirking, okay? So this is the minimum bonus payment that I need to offer contingent on success for agent I to be willing to work given a ranking belief mu I. Now the principal is going to make this bonus payment only in the case of success. And so if I multiply by P of n, which is the probability of success, given again that all agents are working, I'm going to have this function that we call fi of mu I. And this is the minimum expected fee that the principal has to pay to agent I when his ranking belief is mu I. Okay, so this is the function that we are going to use from now on. And so because we know that the principal can simply search over the set of ranking schemes, his problem is to find a ranking scheme that minimizes his expected cost. And I can now write the expected cost as I have here at the bottom. I'm adding over the agents, what is the expected fee that I have to pay them, taking the expectation over the types, okay? So this is the principal's problem. And when we look at the problem written in this way, we realize that the key choice for the principal is a profile of distributions over ranking beliefs, right? But the principal is constrained. So the principal cannot make an agent believe that he's placed very late in the agent ranking, which would allow the principal to lower the bonus payment that he has to offer to that agent, without making some other agent believe that he's placed earlier in the agent ranking, right? So there is some order. Someone has to be placed earlier if someone is placed later. And so to incorporate that constraint in the principal's problem, a useful interpretation of the principal's problem is the following. We can think of the principal as choosing an average ranking distribution plus an information structure, where the information structure which will tell me what each agent is going to be learning about the realized ranking from his realized type, okay? And the reason why this interpretation is useful is actually that we find that the principal's problem reduces to optimizing only over the average ranking distribution, which means that the principal does not benefit from providing agents with any private information about the realized ranking. And so that's our first main result. This theorem says the principal's optimal value is to find a ranking. This is the one that solves this problem. So this is the auxiliary program that I was mentioning before. The principal is going to choose a ranking distribution mu in order to minimize the sum of these fees fi. Okay, and so the main takeaway here and the way we prove this is there are two steps. So first, what we are showing is that the principal does not benefit from giving agents any private information about the realized ranking. And that follows from the fact that this function fi of mu I is going to be convex, right? So if we go back for a second here, we can see that this is a convex function of the agent's ranking belief mu I. And so what that means using Jensen's inequality is that the principal wants to assign the same belief to any two types of a given agent, okay? Now, of course, the principal doesn't benefit from giving any private information to the agents about the realized ranking, but that doesn't tell me that the principal can achieve in this way any ranking distribution that she wishes to induce. And so the second part of the proof is constructive, and it shows that give me any ranking distribution mu, I can construct a sequence of ranking schemes with limit cost equal to the principal's optimal value that gives no private information to the agents with probability approaching 1. Okay, and so to illustrate that, let me go back to our simple example from the beginning where we had only 2 agents. So remember, we had agent 1 had 2 types, so he could receive either the high or low bonus, and agent 2 had only 1 type, he was offered the medium bonus. And so basically what we were doing in that example was to randomize over these 2 edges here, and we were randomizing uniformly. Now, it turns out that here only agent 2 is facing uncertainty about his rank relative to agent 1. When we solve for the principal's optimal value, we are going to find that this is not an optimal scheme because the principal's optimal value actually pays BM to each of these 2 agents, right? But we can, there you go. We can approximate that optimal value here by basically just adding types. And so we can create uncertainty for both agents regarding which one is ranked first. And so now I would be randomizing over all these different edges. So the lowest type would have to be offered the high bonus, the highest type can be offered the low bonus, and all types in between would be offered the medium bonus. And so this is a ranking scheme, so we know that it uniquely implements work. And if I keep adding types and I keep adding edges as a result, then we'll have that both agents are going to be paid BM with probability arbitrarily close to 1. And so, you know, the proof in the theorem shows, so here what I'm doing is achieving a ranking distribution mu that is going to draw uniformly from all these edges. So that's the one that, as we're going to see next, is the optimal one for this example with symmetric agents. But of course, I could do this in different ways to achieve different ranking distributions that I want to induce. And so the construction in the theorem shows that for any ranking distribution mu, I can always construct a sequence of ranking schemes that approximates that. So I'm looking at my clock. So yes.
Sorry, it's very interesting, but so the question, I mean, so it seems like in this example, maybe more generally, you need to create this very long chains of iterated deletion. And so I'm just wondering, you know, in general, well, we think people don't follow long chains. What if there's some kind of failure of common knowledge or something that how, like, what having the kind of, it seems like a very long chain that might not actually happen.
Yeah, so my view on this is that, I mean, in some sense, this is why I wanted to start with a simple example and a simple scheme, which is not optimal, that I show you. Because I think that this is a bit like, as you're saying, like common knowledge of rationality, right? Do we think in the limit? Do we believe it? But that doesn't mean that this is not a useful concept, right? Because we don't need to get to the limit for this to be useful. And I guess I'm trying to convince you of that, right? So that's why I started with that simple example where I don't have this abstract construction that it would be hard to believe that people can follow, but I'm still showing you how I can both reduce the principal's cost and reduce discrimination, right? And so I still, I think as theorists, we are still interested in the optimum. And so yes, you are right, in the optimum, I have to do this limit. But I think there is still value because this holds even for a very simple example, as I showed you. Yeah. So, but thanks. And I guess here is where the commitment to the randomization, you can see how it's not problematic, right? But let me discuss that later, so I can show you the results. But this is the part where I was going to make the point on that. Okay. So I do want to at least mention the other results. So what we also show is that this auxiliary program that we derive from the principal is also going to give us a characterization of optimal incentives. In particular, what we show is that there is a unique bonus profile B star that solves the auxiliary program, right? That minimizes the sum of payments, and a sequence of incentive schemes sigma M that uniquely implements work is optimal if and only if it induces a bonus distribution, which converges to a degenerate distribution on B star, okay? And so, in other words, this is telling us that the optimal bonuses are approximately unique and that they are going to change continuously with the model parameters. Both of these are in contrast with the case of public contracts. A key corollary of this theorem that we are particularly interested on, given the current debate, is what we have to say when agents are symmetric, okay? So what do we have to say about discrimination? So let's say that agents I and J are symmetric if they have the same cost of effort and the same marginal product of effort, no matter what who else is working. And then what we find is that if these two agents are symmetric, then a sequence of incentive schemes that uniquely implements work is optimal if and only if it induces bonus distributions for these two agents that converge to respectively B and degenerate distributions on BI star and BJ star, where these bonuses are equal. So we obtain no discrimination between identical agents, nearly no discrimination between nearly identical agents. And what is key here is that the principal is allowed to induce this rank uncertainty, right? And so again, this has to do with the convexity of that function Fi that we saw, which is going to tell me, as I anticipated before, that when agents are symmetric, I want to provide this assurance to each other about the other worker working in a mutual way. Because an agent's incentive to work is going to increase by more when he believes that the other agent is working if he was initially very pessimistic about the other agent's effort. And so when agents are symmetric, I want to induce them to have exactly the same beliefs about each other's ranks, and hence they're going to be demanding the same bonus to work. And of course, this is in stark contrast with the case of public contracts. So before I jump to conclude, I'll show you one more set of results that we have in the paper. You know, as I said, we are particularly interested in the case of symmetric agents because we think there is an important discussion to be that we should be having about what drives discrimination in firms, pay discrimination. But we're also interested in understanding what happens when agents are not symmetric, because agents differ in their skills. And so to solve this problem, we take a symmetric production function, namely, we assume that the probability of success depends only on the number of agents who are working and not their identities. And then the heterogeneity is only in the cost of effort, okay? So I'm going to order my agents in increasing cost of effort. And this is what we obtain. We show that there is a weak order on the set of agents, such that if agent I is ranked ahead of agent J in this order, then every optimal ranking distribution will rank agent I above agent J, in the sense that there is going to be no uncertainty from the respective ranking distributions that I is ranked ahead of agent J. Now, if this is the case, it has to be that agent I's cost of effort is lower than agent J's. So let me just tell you the idea here. The idea is that, as I said, because of this convexity, the principal, there is this force that says that I want to reduce differences in agents' beliefs, and that's the force that takes me to uniform beliefs and equal bonuses in the case of homogeneous, of symmetric agents. But now, suppose that an agent has a higher cost of effort. That means that for any ranking belief that the agent has, his incentive constraint is going to be more demanding. So what the principal wants to do is adjust ranking beliefs in order to provide this higher cost agent more assurance that other workers are working, and hence relax his more demanding incentive constraint. And so the way to do that then is to increase his belief that he's ranked later, he's placed later in the agent ranking, so I can reduce his bonus. And so what this tells me is that there is this trade-off now between providing this rank uncertainty to reduce differences in beliefs, but at the same time tailoring ranking beliefs to relax incentive constraints of lower skill agents. And so what we show, and I won't go over the details here, is that the degree of rank uncertainty that the firm wants to induce is going to depend on how different agents are. When they are very asymmetric in their cost of effort, I'm going to rank them in order to provide assurance to the higher cost agents. But if they are similar enough, I'm going to induce rank uncertainty among them. And so I'll just advertise, because I don't have time to describe, that what this gives us is the idea of an organizational hierarchy where agents of similar skill are assigned to the same hierarchical level. They face uncertainty about their relative positions, and they have their compensation depend on their relative skills. And then only agents of sufficiently higher skill are going to be publicly assigned to higher hierarchical levels, and they will have their pay be independent from the cost of those in lower levels. And throughout, the firm is going to reward higher skill agents with higher rents, namely with a higher bonus per cost of effort. All right, but I ran out of time. There are some very cool extensions that we analyze in the paper, and I just want to jump now to the conclusions. One main result we have here is that rank uncertainty allows the firm to ensure work at a lower cost. We also have the result that by introducing rank uncertainty, the firm can eliminate discrimination. Now, there is an important debate out there, and there are important concerns about pay discrimination in firms that have led, that have motivated new regulation to increase transparency in firms. So there is new regulation trying to protect workers who share their contract terms, and some firms are now moving to more open internal disclosure policies. And so we think that we can bring a new perspective on this debate, because what we show is that from the viewpoint of optimal incentive provision, lack of transparency does not imply discrimination. To the contrary, together with the results of Winter, we find that discrimination is optimal if and only if the contracts are required to be public. And so the practical implication of this is that either these measures aimed at improving transparency will be counterproductive at reducing discrimination, or factors different from optimal incentive provision are behind firms' discriminatory policies. And we think this is an important distinction to be made, that once we allow for these contracts to be non-transparent, optimal incentive provision cannot be the reason behind firms' discrimination. And so with that, apologies for 2 more minutes. Thank you very much.
No, thank you very much. That was exactly on time with the introduction. So thank you. So now we have the Q&A part. So I'm going to start with Ilya, if he has any comments. But yeah, to the attendees, you can still post questions in the Q&A, and we will allow you to speak, or if it's too cumbersome, you can also just raise your hand if you want to ask a question in person. But yeah, first, Ilya, if you have any comments.
Okay, I have a few short ones. Actually, in terms of the literature, there's a paper in 1984 by Mukherjee on implementing efforts and teams, and also has this kind of divide and conquer thing there, that you want to make it sometimes a dominant strategy for one agent to work hard, and the other will have a best response. So that also, so it's kind of an older idea in that sense. But also I thought about, he looked, I think, at risk-averse agents. So you think, well, what if agents are risk-averse? But it's interesting, I think, which I didn't expect in the beginning, that in the solution, you think if agents are risk-averse, you don't want to subject them to this extra risk of, where they are. But it turns out the risk has to be infinitesimal, right? Anyway, I mean, you could make it infinitesimal. right? So
right.
that,
It's actually, we don't analyze this in detail in the paper, but actually, if you think about, because everything is, everything comes from this convexity of this function fi of mu I that I defined, and actually that convexity, you know, would actually be emphasized by agents being risk averse, and so actually we can show that even if we introduce risk aversion, our results would go through. So that's kind of a very broad intuition, but yeah, we could show more on that.
so you get the same result. I mean, risk aversion is just pushing you more towards infinitesimal risks, right? That's what you said.
Well,
right?
not necessarily, because it makes the function fi potentially even more convex. So you know,
No, all right. But I mean, you had the theorem.
I don't know if
that
I would
said
have a measure to answer that question correctly, but I can think about that.
No,
I don't know exactly what metric I should use, but I don't want to say.
But so the theorem said that, you know, in the limit you converge to a kind of deterministic scheme, right? So that you can make.
In terms of in the limit, if you take the limit, then basically the bonus, we know it's BM. Yeah, the probability
That's right. And that would be presumably, the theorem would presumably be still true with risk averse agents, because that's just another force towards. Right. Okay.
Yeah, that's a good point. Yes.
Okay, so that just okay, so that's nice. Now on this transparency thing, so like if you have a law that says with probability 0.9999 things have to be disclosed, then you can still do exactly the same thing you do, right? Because it's enough to have. Would that work?
With probability 0.999.
You know, the bonuses have to be disclosed.
Yeah, I think.
And then, so in that sense, all.
But what do you mean by that? I'm not sure I follow the takeaway.
I mean, if you change your game that says, you know, just say, well, you know, the queue is chosen, then there's a draw of the bonuses. With probability 0.999, the bonuses are disclosed, otherwise they're not disclosed.
What does disclosed mean? You know,
well,
like
no,
the agents observe them.
If it means
so actually,
oh, sorry.
No, so I don't think that's correct. So let me just say the following. So no, that's not correct because of the following. So it's true that I'm doing the approximately optimal scheme, but when I take a sequence, I'm taking a sequence of ranking schemes. So at each stage of this sequence, I'm uniquely implementing work. And that would not be true in what you're suggesting, right? Because even if I have a tiny probability of the contracts being publicly revealed, and I want to always uniquely implement work, then I have problems. So it's not the same, yeah. I'm always uniquely implementing work. The approximation is only in the value, right?
No, but okay, so actually what I meant is not this, right? So of course, if they're publicly disclosed, that doesn't work. But then you say, well, probability 0.99, each agent privately is shown the others bonuses, but then the others don't know. So there's no common knowledge. As long as there is some, as long as it's not common knowledge with probability 1, you can still do it. Right? Obviously, once you get the common knowledge, things fall apart.
Right. But let me, if I may, let me use your question. That's an interesting point to kind of say something that I didn't have time to say, which is that, you know, what I take from your comments, actually, an interesting question is, you know, as I say, this literature assumes that contracts have to be public, but I'm also assuming something, which is that the principal is able to limit the information that agents have about each other's contract terms. And so what Ilya is saying here about what about an agent going and showing the contract to another agent, right? And in fact, this may also help us understand why are firms insisting so much about these contract offers not being shared among workers, right? Why are they threatening to punish anyone who shares their contractual terms? And so what we analyze in the paper is what would happen if workers can voluntarily and verifiably disclose their contract terms to other workers. And what we can show is that we can always construct an equilibrium where workers will be sharing those contract terms, and as a result, we'll have the complete information game being played. And as a result, if we are thinking about unique implementation, you know, the principal cannot do better than under public contracts. And so this may help explain why firms insist so much on these contracts not being shared. You know, and in relation to also what Ilya was saying.
All right.
All right, well, let's hear the other comments.
Thank you. Yeah, so we have one question from the audience, from Ada Gitmes, who's now should be able to speak.
Hey. So,
hello. I can't see you though. Let's see.
Doesn't matter.
There, I can see you now.
That's the important part. Yeah, so I'm just wondering, so suppose that there is like the firm is constrained by a law that says that ex post, the bonuses of two agents cannot differ by more than a certain amount, right? There's like a discrimination constraint.
Yes.
I mean, of course, it's going to change your optimization problem. But I'm wondering, so
well, it's going to make it. It's going to impose the no. So I obtain a no discrimination result, whereas that would be imposing no discrimination, right?
Yeah. But I mean, so
Okay.
the non-discrimination result only applies for the symmetric agents, right? So I'm asking about in general.
Well, right. So we think, so our definition of discrimination is treating two agents who are symmetric differentially. If two agents are not identical, then treating them differently is not discrimination. You know, it's a different thing. It's basically compensating, rewarding an agent for having higher skill than another agent. So that's not how the literature and I would think of discrimination. Discrimination is treating differently two agents who are not different, right?
Okay.
So that's why when I talk about discrimination, I think of symmetric agents.
Okay, then let me put it this way. Let's not think about discrimination, but the firm has an incentive to sort of keep the bonuses as similar to each other as possible, right?
Mm-hmm.
I mean, indeed, like there is like an ex post limit on the firm that says that you cannot disperse the bonuses by more than this amount, right? So it's just an constraint on the firm's optimization problem, right?
Okay.
So you have an optimization problem there that says there is an objective function and subject to the UIW constraint.
Okay.
Right. So I'm just wondering that, so I mean, this is going to change the optimization problem. It's going to come as an extra constraint to that problem.
Okay.
But this might be the only way that it changes this optimization problem, or it might also affect the earlier results that says that anything implementable that I can do it with this, and etc.
Well, it will, if we are talking about public contracts, it will change things dramatically, right? Because if I need to uniquely implement work without discriminating, let's take the case of symmetric agents to make it simple, then what that would imply is that I have to offer the high bonus BH to both workers, right? Because I cannot discriminate and I want to uniquely implement work. So the firm's cost would go up significantly. In our case, by taking symmetric workers, this would not have much bite because in fact, the firm finds it optimal to offer the same bonuses to the agents, at least in the limit. This is what the firm is doing without the constraint. Now, away from the limit, you know, I have to solve it. But clearly, in any case, you know, it would have a larger effect in the case of public contracts where I have the need to discriminate in a significant way across these agents in order to reduce the cost of uniquely implementing work.
Fair enough. Thank you.
Sure.
Right. So are there any other questions? There's Francesco. Let me make him a panelist. So yeah, Francesco, I made you a panelist. So we have time for a quick question, if you can.
That's the Francesco. Where are you, Francesco?
Francesco Squintani. Yeah.
Yes, I can see his name now.
Hi, Marina.
Hi, Francesco. Good to hear you.
Nice to hear you.
Long
Great
time.
talk as always.
Oh, there you are. How are you?
I'm fine, thank you. Great to see you. And great talk as always.
Thank you. Thanks very much. We didn't arrange this, I promise. He's my friend, but we didn't arrange this.
Now, I was wondering if instead of looking at the unique implementation, you allow for Bayesian Nash, then because I mean the fact that ranking, if I understood, the ranking contracts being these are the unique. I mean, there doesn't exist any other contract that lead to unique implementation that is that is less costly than the ranking contracts. This is your result, one of the building results in the literature, I guess. if instead of looking at unique implementation, you allow for multiple equilibria,
then in that case, if I only want to induce an equilibrium where the agents work, there is no scope for beneficial rank uncertainty, right? So basically, in that case,
I mean, it is known what happens.
No, well, it's actually, so think about the very simple example, right? Where I have these two workers. If I only want to induce an equilibrium where both workers work, I offer them the low bonus BL to each worker. There is no way I can offer a worker less than that, right? So because he has to have incentives to work conditioning on the other agent working. So in that case, we don't have much to say here.
I see, because then they either coordinate on both working or both coordinate or both not working, right? And this comes from the complementarity in
that's exactly right.
Okay.
That's exactly right. Yeah. So there is a question about what happens if I don't have a supermodular production function. That's another extension that I skipped that I can now advertise.
Sure.
So if you go to the limit of having a submodular production function, then unique implementation has no bite. So I mean your work basically to induce work to be the unique equilibrium. I need to induce it to be. So whenever I'm inducing work to be an equilibrium, I'm going to be inducing it to be the unique equilibrium, right? So again, rank uncertainty has nothing to do here. But then if I have some complementarity, some substitutability, so that the production function is neither supermodular nor submodular, then our analysis does provide insights. Rank uncertainty can have an important role. We cannot solve, or we didn't try a lot, but what our analysis most directly is going to imply is insights for how to solve for the optimal scheme that implements work as a unique rationalizable outcome. Now, as Ilya also was commenting before, if we don't have a supermodular production function, then this is not the same as unique equilibrium. And so, there is the question of whether you could do better when requiring unique equilibrium implementation as opposed to rationalizability. But if you care about unique rationalizable outcome, then our insights actually translate quite directly to that case.
Okay. Very nice. Thank you.
Thank you.
Sorry. Okay, thank you very much. So we've run out of the official time. So I want to thank Marina very much for her presentation, and also Ilya Segal for being our expert panelist, and also Marina's co-author Elliot Lipnowski, sorry, for helping us out with the questions. So this was the final seminar before the break, and we hope we'll be back after the summer. Thank you very much.
Thank you very much. So thanks a lot for having me. Thank you, Ilya, again. Hope you can have breakfast now. We'll have lunch. You guys will have dinner. So thanks all for tuning in despite the time differences and all.
Thanks.